All right, let's do section 9.3, page 461, number 5, which reads, show that the natural log of x grows slower than the function x minus the natural log of x. So we're going to start by letting f of x be equal to x minus natural log x, and we're going to let g of x be equal to the natural log of x. So we learned earlier that if g of x grows slower than f of x, then the limit as x goes to infinity of g of x over f of x is going to be equal to 0 if g of x grows slower than f of x. So let's substitute our functions into this limit and see what kind of an answer we get. So I'm going to have the limit as x goes to infinity, and for g of x I'm going to substitute in natural log of x, and for f of x I'm going to have x minus the natural log of x. And of course the first thing I do when I come to a limit is I'm going to substitute in. And when I substitute in, I end up with infinity over infinity, which is an indeterminate form. And it happens to be an indeterminate form to which I can apply L'Hopital's rule. Now when we have L'Hopital's rule, we continue to have our limit as x goes to infinity. And then I take the derivative of the numerator separately from the derivative of the denominator. So what's the derivative of natural log x going to be? Right, it's going to be 1 over x. And then in the denominator, I'm going to do a similar thing. I'm going to take the derivative of the denominator and put it into the denominator. So what's the derivative of x going to be? 1. And then again, the derivative of the natural log of x is going to be 1 over x. And now I can substitute in for my limit again, but this is looking kind of nasty, so maybe what I need to do is a little bit of algebra here. So I'm going to take the limit again as x goes to infinity, and I think what I'm going to do is I'm going to find a common denominator in the denominator, and that common denominator is going to be x. So I'm going to have x minus 1. And then this is pretty cool because I can actually take this one over x and this one over x, and they're going to cancel. So I'm going to have the limit as x goes to infinity, and what I'm really going to have is 1 over x minus 1. And when I substitute in for my limit, I'm going to have 1 over infinity, which of course is going to give me 0. And if that meets my initial condition up here, which says the limit as x goes to infinity of g of x over f of x is equal to 0, then that tells me that g of x is going to grow slower than f of x, or the natural log of x will grow slower than x minus the natural log of x, which is what we were supposed to find in the first place.